All right, welcome. It's Tuesday, March 24th. So today we'll talk about a moving charges through magnetic fields, right-hand rule number 3, and we'll be pretty much done with chapter 29, and we'll start moving towards chapter 30, which is probably the most interesting chapter, electromagnetic induction. Should one at the you can also run ads whenever you want for money. No, I don't really want to run ads during the stream. The one ad at the start when you log in is whatever. I don't even know how you can stop that. I guess you can't. Um, but yeah, so today we made affiliate, and so that comes with new features in that we could probably make like emotes, our custom emotes. I don't know how to do that yet. So can we get, yeah, like I don't know how to make emotes. If you can figure that out, maybe we can make our own. Perhaps like a little thing. We'll start with John's emote, the logo thing that he made for our shirts this year. Yeah. So we'll do that. If you can do that, then we can have our own emote. That'll be cool. But anyway, today is all about moving charges. Moving charges. So let's begin. Go ahead and take out your notes. Where are we? Here we go. We'll start with source of B. Okay, moving charges. This is magnetic field around a moving charge. What about the physics logo? I don't know. I mean, would you actually use that in chat? Like, I don't see our physics logo being used in chat, whereas, you know, typically your emotes are like weird faces and stuff that you make for reaction, right? So if you had like an interesting point or something, then you can use, you can use the face emote that we have. All right. Anyway, moving B around a moving charge. Okay. We know that the charge will have an electric field around it based on what kind of charge it is. The electric field emanates, away from a positive charge and of course towards a negative charge. Now, if the charge is moving through space, it also kind of flutters and oscillates the magnetic field at the same time. There should be a question mark emote and an I get it emote. Yes, that's what we need. So if you can figure out how to actually do that, is it just uploading a picture or something? Or I might look into it, but I'll need you to like send me. Let's put Nishake on this. If people send you emotes, go ahead and figure out which ones are the best, and then email Nishake. You can email them to me, and then I'll upload it. You need to get them approved. Approved by Twitch? Yeah, that's pretty easy. Oh, Nishang would take 3 years to get that done. No, I'm sure he's checking the ECR physics email all the time, looking for videos to post on our Twitter. So Rebecca's not like on her own trying to do everything. Right, Nishank? Right? There's a dog emote. He's not even here. Oh man, excellent. Just FYI, our final is cumulative. Our final is cumulative. Don't just stop just because the AP said so. FYI, for your information. All right, let's move on. Get it? Let's move on. B. So recall that we can use Biot-Savart law for magnetic field at a close proximity around a current carrying wire. Okay, it's really easy to do all this from a macro scale, and then once you have your macro scale done, then you kind of go into the micro scale and figure out what is really happening, right? Now, current around a current carrying wire produces a magnetic field around it in concentric circles. Of course, as you expand outwards, as the distance away from the wire increases, the magnitude of the magnetic field decreases, of course. Similarly, we can say that the magnetic field, if we look at the wire as current, and current is just charge per second, moving charges at some velocity, we can replace our equation to mu naught over 4 pi times 4 pi r squared, r being the distance away from the charge now. Instead of current, we're going to use Q and V. And of course we need the sine theta, because it is technically still a cross product. Okay? So if some charge is moving with velocity to the right, just like, let's make this positive. Just like using right-hand rule number 1, you would orient the thumb. The thumb is now velocity instead of current, and the curl is your magnetic field. Okay. That's a questionable face. I don't know what that face is. How do you get these? Oh my dog. I guess you sub to some other channel and then you get to use it anywhere? I guess so. So we need to make our own. Let's make our own. Spread the word of physics. Oh, some are generic. Okay. Alright, let's take a look at this. How is this different? How is it the same? We have Q over here, we have velocity over here. Of course, velocity is meters per second, right? Which is the same as some sort of distance over time. For distance, I used L this time strategically. Okay. If you replace velocity with L over T, notice how you get L in the numerator and T in the denominator. Now you have Q over T. Chat, what is Q over T? Tell us. Oh, some students have been saying that the delay is kind of long today. I don't know why. I thought it's like 3-second delay. We'll see. Maybe we'll do we're gonna do like a Kahoot or some sort of review game at some point. So that'll tell us how our delay is. Yes, it is I, the current. So you can have mu naught I, and the leftover is L. Mu naught I L sine theta over 4 pi r squared. Oh. Yes, Q over T. Hey, who are you calling a boomer? So it's the same thing, but now we've kind of replaced it for charges. Okay? So have this down. You'll need it for your homework at least. Alright. Now charges, when going through an external field, just like putting a wire in an external field, recall the example we did with a horseshoe magnet and a wire that is running in the z-axis through the horseshoe magnet, experiences a force. Similarly, a moving charge also experiences a force. This is right-hand rule number 3. Okay, man, we only have 10 people today. This is sad. We're losing our numbers day by day. Day by day. All right. Right-hand rule number 3. So it's the same, except we're going to replace current with velocity. Whoa, that's too long. Let's try again. I don't like this. This is so hard. That's good enough. We have really long fingers. All right. Let's see yours, Mark. Let's see yours. Share. Why don't you share? All right. So magnetic field is still upwards. Pew, 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 pew. And the velocity is now to the right. And of course our force is coming out of the palm. The Buddhist palm technique. No current can be in a still charge. Correct. Current is charge per second, so the charge has to be moving. Why would a charge not move? Well, charges won't move if there's no voltage difference between the 2 points. So if there is a voltage or a potential difference across 2 points, then the charges will naturally move. From positive charges will move from high potential to low potential. And that movement of charges is what we call current. And therefore, current by definition is moving charges. Excuse me. All right. So this is the same thing. All you did was replace current with velocity, and that's about it. Now, if you have negative charges, this is for positive charges. This is for positive charges. Oh, by the way, Jacob, your IP should be unbanned, so you don't have to use your VPN. What do you do for negative charges? So for negative charges, use the left hand. LHR. Or just do the right hand and then multiply your answer by -1, flip it 180 degrees, and that should give you the same answer. Okay. So to simplify, the force is equal to QV cross B. So charge times velocity cross the magnetic field. Now, if you know that they are nice and perpendicular, or you know the angle between velocity and magnetic field, you can say that it's just QVB sine theta. If they're perpendicular, sine of 90 degrees will give you 1, so it's maximum force. How is this different from the other right-hand rule that was QV cross B? What in the what are you talking about? This is right-hand rule number 3, yes. 11 seconds late, yes. Okay. All right, so number 3 is just like number 2, really. It's just that instead of having a full wire that is experiencing the force, we're just looking at one small particle, one charge. We replace the current with velocity. Sword hero, wow. All right. So let's go and do a quick example. Okay. Oh wait, I'm the only C kid that watched Torbo's conference. Torbo's conference? What is this first? Oh, you're... Oh, wow. You get a little badge. That is... All right. Keep your money, man. Keep your money. uh... All right. Anyway... Oh, it's free? Okay. If it's free, then go for it. Okay. So let's do a quick example. Again, in order to feel this force, there has to be an external field created by something else. And it's the internal field created by the charge that kind of interacts with the external field, giving you the force in the first place, kind of like having two magnets next to each other. Let's go and draw a bunch of circle with dots. So dot, dot, dot. Chat, what does this mean when I have a equal spacing between all these dots? Go ahead and describe what I am drawing here. Okay, keep going. A little bit more specific. We got uniform magnetic field. Okay, more words. Out of page. Excellent. This is a uniform magnetic field that is out of the page. Stephen Gong gets the whole thing. Wireless high five for Stephen Gong. Actually, we need a wireless high five emote. Can someone make us a wireless high five emote? Oh, here's Sword Hero again getting blocked. This is rigged. Why is it rigged? Someone make me a wireless high five emote. Oh, there's Nishank finally waking up. All right, so we have a uniform magnetic field that is pointing outwards out of the page. Okay. Now, the real question, how can I make a uniform magnetic field going out of the page here? Right. For electric field, we can use parallel plates and use, and in between parallel plate capacitors, we know that there exists a uniform electric field. But how do I make a uniform magnetic field? What is this? Have a solenoid with coils on the XY plane. Excellent. That's exactly what we did yesterday. If you look through a solenoid through the z-axis now, based on how you send the current in, you can get a nice uniform magnetic field inside the solenoid. It only exists inside the solenoid. Genius Alex Rank, what did he say? Oh yeah, he's the one who said the solenoid. Very good. Oh, what's this other one? Horseshoe magnet, question mark? Technically, yes. If you have a large horseshoe magnet, then that small region between the two bars. So just in this region alone, you would have a nice uniform magnetic field. All right, anyway, look up Twitch emote specifications. Ooh, someone has a wild plate. I was going to say horseshoe magnet, but doesn't one end of it have to be behind you then? Well, you can orient it in the z-axis, and we would just look at a cross-section in the middle. So if you look at the cross-section as you orient the horseshoe magnet coming out of the z-axis, then it's technically magnetic fields coming out of the board. You are the horseshoe magnet. All right, let's go and have a charge flying through. Let's do a positron. A positron is flying through this uniform magnetic field. And we want to make sure that the uniform magnetic field is big enough, so make it large. All right. Using our right-hand rule number 3, which way is the force on this charge as it moves into this uniform magnetic field to the right? Okay, so this is where you keep your hand flat, Make sure your thumb is 90 degrees to your fingers. Your hand is flat. You want to point your thumb to the right because that's the direction of the velocity. Velocity is to the right. And we need to orient our fingers. We need to orient our fingers so they come out of the page, out of the board. And you'll see that exactly. So you'll see that the palm is now downwards. So it would be negative y. Mystery Wizard gets it. Mystery Wizard. Well done. Velocity to the right. Magnetic field coming out of the page. So that means palm is downwards. So the force is downwards. All right. So now as soon as I enter, let's make sure we understand what that means. It is downwards only at this spot here when it enters the magnetic field. Remember, there is no magnetic field to the left here. Ouch, I poked my eye. Oh, that is unfortunate. So as soon as you're here, your velocity is to the right. Let's go and color code this stuff. V is to the right. We'll use blue for force. Force would be downwards right here. Ah. All right, so what does this mean? Well, as soon as you have a rightward velocity and a downward force, your force and velocity are 90 degrees to each other. What does a force that is 90 degrees to a velocity vector do to the velocity vector? No, I don't want to reduce it. Then we might have people spamming it, and I don't want spam. Ooh, why? No, we want to make our own. We can't just steal someone else's. Accelerates. You're close. You're close. Keep going. Okay. Think. Where have you seen a velocity vector to the right or horizontal and a force vector? Gravity. Force vector pointing downwards. It's in UC. No, stop saying UCM. I just want you to. Just because you know the ending to a movie, it doesn't mean you understand the actual story, right? So we want to make sure we understand the story first. Well, forget about the ending. UCM? EM? UCM? I don't know what you're saying. Kinematics. Ved Kulkarni. Throwing an object off a cliff. Excellent. We call that horizontal or range equation stuff, right? As soon as you're at the top of a parabola, you have a velocity vector Vx to the right. Your gravitational force vector Fg is downwards. So what did the force vector do to the velocity vector? Stop, Stephen Gong. That's all from studying from the SAT test. I want you to follow along. The understanding is more important than just, than what you typed. Angles in downward. Okay, when your acceleration vector, essentially your force vector, is 90 degrees to your velocity vector, the force changes the direction of velocity only. It does not change the magnitude. The force changes the direction of velocity only. It does not change the magnitude. This is why I want you guys to follow along. Forget about what it equals for now. Understand it first. Okay. So as long as force is 90 degrees, then it will only change the velocity vector's direction, not the magnitude. However, you'll see that after you make that change, when you're at position 2 in parabolic trajectories, the velocity vector is now sideways, tangent to the parabolic arc, and the force vector is still downwards, FG is still downwards, and now the angle is not 90 degrees. Okay. Therefore, after you pass this midpoint on a parabola in a parabolic trajectory, the force actually starts to accelerate your object. Your velocity starts to increase. That's why your minimum speed is at the top, and then as you grow, as you pass this midpoint, your velocity starts to grow and get faster and faster. Okay. All right. Now, back to here. Back to here. All right. The velocity is to the right, and at the start, the force was downwards, straight downwards. And we know that when it's 90 degrees, it's going to go in some sort of parabola. It's going to dip our velocity vector downwards, which means it wants to go right, but it's accelerating to downwards. Therefore, the velocity vector, once it's here, it will turn a little bit. It will arc. Okay, so we start our arc. One small delta t amount of later, one infinitesimal time frame later, we are now at this position. I'll use blue. We are now at this position. We kind of arc downwards. Okay. Now that we're at this position, okay, our velocity vector is angled a little bit. It's this way. Question, chat. Which way is the force vector? Is it downwards or something else? Ooh, let's do a quick poll. Vote 1 for downwards. Vote 2 for something else. Edit FB. Is there a way to edit old choices? No, it's not. Vote 1 for down. Vote something else. Something else. Vote 2. Add. Done. Start poll. Boom. Wait. Now it started. Now you can do it. Is it working? Can you see it? Whoa, look. B is always the same. B didn't change. Look at the picture. B didn't change. Ten, 9, 8, 7, 6, 5, 4. Liam is in Minecraft. Liam, stop playing Minecraft. 4, 3, 2, 1, 0. Complete. Whoa, we got 100. Let's do 100. Hype train. Can we get 100 in the type in the chat? 100. All right. You would orient your thumb at an angle, but your fingers have to point out of the page still. You'll see that the palm is now pointing. What's our color for force? Oops, I used different colors. This is velocity. And our force would be this way. And you'll see that the force is always, no matter how much you turn, the force is always at a 90-degree angle to the velocity vector. And since the force is always 90 degrees to the velocity vector, it will always change the direction of the velocity vector, and it will keep the magnitude the same. And thus, based on how big or how fast, how big the magnetic field is, or how fast your charge is going, you can create a half a circle depending on the radius of the circle. Or, if you're not going fast enough, then you can basically create a circle inside, and it'll stay in UCM. Now, how do we know if we're going fast enough to create a circle or not? Well, we have to use our FBDs. Okay, so let's figure out the relationship between the radius of the circular arc and the actual velocity of the object. Okay. Yes, FBDs. Yes, even in magnetism, you never stop. So if we are going in a circle, well, that's terrible. Let's do ink to shape. Yay. If we're going in a circle, let's say we're going this way. Okay. We can see how the only force that we have, let's say we're over here, the only force that we have is the magnetic force FB. Okay. So if I did my sigma equation next, sigma F is equal to the magnetic force, and there's nothing else, assuming, we're just on our own in outer space. Perfect circle challenge. Hashtag perfect circle challenge. Yes. What is the right side of our equation equal to if we're going in a circle? Sigma F is equal to FB, which must equal, right side of the equation, mv squared over r. mv squared over r. Yes, it's UCM. It's centripetal acceleration, Mach. All right, so now we replace our force equation with the magnetic force formula that I just gave you. It's QVB sine theta. What is the angle between velocity and force, no matter where you are? It is 90 degrees, and sine of theta would give us just 1. So we can just ignore the sine of theta. So QVB must equal mv squared over r. One of the v's cancel, bam and wham. Oops. There we go. This gives us the formula for radius. So the radius must be equal to mass times velocity divided by charge times magnetic field. Yay, we did some honors physics level stuff. You'll see that we learned this in honors physics as well. 450? What? Stephen Gong being clever. You're insulted. Hey, we got to start somewhere, right? Well, okay, you shouldn't be insulted. That's just, the reason why we're doing it is because this is a classic physics problem. And that's why we did it. It shows us that even though we're doing magnetism and all this weird stuff, all the things we've learned thus far, all the mechanic stuff still applies, right? Physics works all together. It's not just one at a time. Classic. There you go. You happy now? All right. Okay, so based on my velocity, we can see how the r is proportional, directly proportional to the velocity. Okay. All right. Sometimes this is called a cyclotron, where you can spin things around. Using magnetic fields, this is how we separate high level, isotopes, for radioactive, if you will, during the World War II, when we had to isolate uranium and stuff, we would use a magnetic field. So this way you're basically playing marble in a cup with magnetic fields to send different objects at different radius or different trajectories. Pew, pew, right? Marble in a cup. So you can separate your particles When Marvel in a cup destroys the world. Pretty much. So, let's see. Let's say you have the same charge in your isotope, right? Let's say you have the same charge in your isotope. Which variable will account for the difference in the radius of each trajectory? If you're trying to separate isotopes. No. Not Q. I just said if they're the same charge. Remember, what are isotopes? AP Chem students, please tell us what isotopes are. M, yes. Isotopes have different numbers of neutrons, so their masses are different. Okay, now the real question, if the mass is more, if you have a heavier isotope, will the curve be smaller or bigger? Will my circle be smaller or bigger? Now I also have to make sure that they're charged in order for this to work. Yes, look, M is in the numerator. So with a bigger mass, it's going to curve more. You could also think about it in terms of inertia. Something with more mass is going to take longer. Something with more mass is going to take longer to turn because it has more inertia. It requires more force. Therefore, it takes much longer path to curve because it's harder to turn. Imagine trying to hold onto a rope while turning a bus versus holding onto a rope turning a skateboarder or a bicycle. What? So the difference is just V over QB del M. Yeah, del M. Okay. Last thing we're going to talk about is torque. Torque. So we're done with charges. We're on to our last topic in chapter 29. Imagine now having your loop. We're going to have a square loop. This is a reminder that you should do your mastering physics because there's this awesome square loop problem. It's really hard. So here's our square loop. Let's go and send current. We'll go and send current this way, up the left one. Alright, so if current is going up the left one, it's going to turn to the left here. So along this wire, current is to the left. Along the left wire, it's upwards. Along the top wire, it is to the right. Along the right wire, it is downwards. Along this segment here is left. And then it will come back down through the other tail. Focus, focus. All right. Now, let's put this loop of wire with current in an external magnetic field that points to the right. I need to draw it in 3D. Oh, shoot. So now let's go and take this in 3D. We'll put our loop through the z-axis. Here we go. So our current is going up the left one, therefore it's up this one, down this one. To the right here. Okay, now it's in 3D. Okay. Let's go and send our magnetic field this way. Like so. This is an external magnetic field B. All right. Okay, take a look at the force on, let's start with the right one. The force on the right wire here. What is the force on the right wire? Current is downwards. Oh no, what did I do? current is downwards. Okay, current is downwards. Field is to the right. Which way is our force? So let's look at it like this now. Pew, pew, pew. Current is downwards, field to the right. Okay, so thumb down, field to the right. It is out of the page, very good. So on the right wire, we have a force that points out of the page. Okay, what about the left one? Ooh. Okay, let's do the left one. On the left one, we have current up, but the field is still to the right. You need your thumb upwards, fingers pointing to the right. You'll see that the palm is going into the page, in the page, yes. So this is going to be circle with an X. So now imagine having a loop right in front of you. The right one is being pulled towards you, while the left one is being pushed away from you. So this causes the thing to spin. We have a torque. All right. So as it turns into this 3D orientation here. Now, what about the top wire? What kind of force is there on the top wire? Current is to the right, magnetic field is to the right. All right, you need your thumb pointing to the right and fingers pointing to the right. Notice how you can't do it without breaking your hand or squishing your, destroying your right hand rule. Yes, very good. It's parallel, so the cross product of parallel vectors will give you 0. Okay, so no force on the top wire and no force on the bottom ones either. Remember, when you're anti-parallel means they're going in 180 degrees to each other. When theta is 180 degrees or 0 degrees, the cross product will give you 0. So there's no force on the bottom ones either. No force. It's only the left and the right ones. Okay. Now, when it starts going through, is there a force? Is there a force? So let's say we are now, we have now rotated 90 degrees such that all of the magnetic field goes through our wired loop. Is there a force on the wires? So when you're in this orientation, we have current downwards while field is to the right. And notice how this would drag this right wire towards you. Okay, let's go ahead and do the back one. Back one. We have current upwards, field, but this back one is being pulled the other way. Circle with an X. So it's trying to stretch it out almost. And these two forces will be equal, therefore their magnitudes will cancel out, and therefore the net force is 0, outwards and inwards. What about the top one? Well, the top one is towards you, while the field is to the right. This pulls on the top wire upwards. But the down ones, remember the down ones have current this way. The downward ones have forces pointing downwards, and again, the forces will cancel each other out. Once you're in this 90-degree orientation, the net force is 0. Oh, sorry, I should say net torque is 0. Because all the force is 0. I should also say, actually, I can say both. Okay. Here, the net force is 0, yes, but the net torque is not 0. Oh, he's right. Yeah, thanks. Thanks, bud. All right, so the net force on the left one is still 0 because one goes towards you, one goes away from you. Those two cancel each other out. Here, everything is 0. So does it go backwards? No, there's this thing called angular momentum. So because it started turning this way, it's going to continue onwards. The angular momentum of the system will carry it through, and it goes the other way. It goes the other way. But then it goes too far. It goes too far. Torcal, no, it's called angular momentum. It goes too far, and then it starts to slow down, and then it oscillates back and forth and back and forth, back and forth. Okay? Now, ideally, we don't want it to go back and forth. We just want it to spin. That's what we called a motor. So strategically, what we have to do, we'll find out next time on Dragon Ball Z. Next time, we'll find out that if we can strategically turn the current off, you don't have to change the current. You could. That's a slightly harder. We're going to do this with just DC power, not AC. So if you strategically turn the current off so that the momentum carries it all the way around to the other side, and then turn the current back on when it flips over 90 degrees from figure 2. Let's call this figure 1. And this figure 2. So if you allow the momentum to carry you 90 more, did I say 90? Yeah, 90 more degrees, or 180 more degrees, or whatever it is. If you can go all the way around, 180 degrees, and turn the current back on, it will continue to force it to spin. It's 180 degrees from figure 1, I guess. It'll continue to spin the same way, and you can get it to spin forever, right? Assuming you have power. All right, so let's do some equations. We got total torque is equal to tau 1 plus tau 2. Okay. Tau 1, actually I'll just write it in, this is pretty sloppy, sorry. Tau is, it's supposed to be a sigma. Tau 1 is the force times, times what? Well, how do we get torque? F cross R, or whatever R is, the radial arm. It's blurry. It should stabilize soon. I think there's a dip in bit rate. Times your radial arm. Your radial arm would be whatever the size of your thing is, divided by 2. So let's call this a square loop, so it's just length L. And so it's square, so everything is square. So this would be L over 2, because it's in the middle. Center of mass. Center of mass. Alright, plus F2. Okay. Notice how they both are in the same direction. The right one is coming out, the left one is going in, therefore the torques are in the same direction. It forces to turn the same way. Now technically, if I look from above, it is going in a clockwise fashion, so we could say that it is negative torques, but I'm just going to leave that bit out. I'll just reverse the direction of my magnetic field. F2 should be the same length divided by 2. We can say that the forces are the same. F1 must be equal to F2. And to find that force, we get the magnetic field times the sine of the angle, B sine theta, IL. F bil is the equation, technically, if you know that it's 90 degrees to each other. F bil, what did bil do? I don't know. And therefore, torque is just F times L, right? F times L. Because the forces are equal. All right. And finally, putting it all together, if the force is B bil or B sine theta ill, and we have L already, we get torque is equal to B times sine of theta times the current times L times L. L times L is basically the area. You have to switch off and on current. You need to switch on and off if you want it to rotate the same direction. Otherwise, it'll go into shim, and it'll just oscillate back and forth. Mr. Z, check your email. I sent you the wireless high five. Very good. We'll take a look at it, and then I'll see what I can do. All right. So we replace the force with Bill. The torque equation has an L already, so now the L squareds give you the area instead. And finally, having just one loop is not enough. One way to increase the amount of torque is to have multiple loops. Wouldn't sigma t be Bill BIL since it's yes. So L squared is area. L squared equals area. Remember, square side length times side length equals area. Very good, Kulkarni. And so to increase our torque, to make it go and turn faster and faster, we can just have multiple loops instead of just a single loop. So let's go ahead and multiply this by n. Let n equal number of loops, hashtag loops. And therefore, your tau would be equal to n times all of this. So I typically write it in this way. I just move things around, move the variables around. Niab, N-I-A-B, sine theta. Niab sine theta is the torque. I'm going to box this thing here. That's our torque on a loop, on multiple loops. We'll also box F bil. This is the general equation. B sine theta ill, if you're at an angle. Okay. And that is about it. All right. Thank you for tuning in. I'll see you next time.